this video we're going to talk about Junos OS fundamentals and high-level overview on how Juniper hardware works. So the idea here is to understand a little bit better how the OS actually works and how packets flow through a typical Juniper device. Of course, this is high-level because every different platform has its own, little things to improve performance. But in a high level, this is the design goals that Juniper has in all the products. So let's talk a little bit about the operating system. So the Junos operating system lives on top of a FreeBSD OS. So FreeBSD is the free equivalent of BSD, which is a Unix operating system. So it has a long history and it has worked over 20 years in many mission-critical scenarios. So that's probably why Juniper chose it to put it on their devices. It's not required to be a Unix expert to be able to configure and use Juniper. Of course, it helps, but it's not necessarily you are faced with a Junos interface, not directly with a Unix interface. So it's fine and it's not required. But it does bring some interesting things to the mix, which is, for example, it's very interesting that in the Junos operating system, every process has its own space of memory, its own single space of memory, which means that if a process has a problem, it won't be able to affect the other one. That's something inherent from the Unix philosophy and the fact that it sits on top of a Unix OS, so it has to follow the same rules that all other Unix processes and Unix applications have to follow, which gives us a lot of stability. So so it's very robust and it's very stable. So another interesting thing is that, for example, all the software on Junos follows a single software train. So what's interesting about that is that maybe I have a J-series router, and if I have a J-series router running, for example, 10.0 or 10.1 or 10.2, and I have an MX router that's running the same software, so it's running 10.0, they basically have the exact same software. Of course, the software has little tweaks to be able to use better the hardware of the MX or use better the hardware of the J-series router. But in essence, they're exactly the same, which means that if you're an end user or if you're like a systems integrator and you train all your people to use Junos on a J-series, they will be able to do pretty much the same thing on an MX. Of course, for very particular things, for very MX particular things, or another platform particular things, you will have to learn a few more commands. But in essence, it's exactly the same. They are managed in the exact same way, the big from the small, which is a very interesting thing because that's not always the case with other vendors. If we take Cisco, for example, since it's the other big networking vendor out there, we see that we have the iOS, we have the iOS XR. If you're using Nexus, you have the NX OS, which is completely different. If you're using Cisco firewalls, they have another operating system. So that creates a lot of disparity because each one of those has its own syntax, its own rules. That doesn't happen in Junos. In Junos, you have a single unified OS for almost everything. So it's very flexible, and it means that, for example, if you're an end user and you start with a J-series, and then as you grow, your business grows, you move into a bigger platform, you move into an MX or a T-series or whatever, you won't have to deploy new tools and you won't have to retrain your administrators. So it's a very nice feature, it's very consistent, and it's very rare, it's quite interesting. So that's the software. So let's talk a little bit about hardware. In Juniper routers, there's typically two components that are very fundamental to understand. And those are the RE and the PFE. So the RE stands for routing engine, and it's the equivalent of, if you come from a Cisco world, of a supervisor card. It's basically the part of the device or a particular card which handles all the control plane, which handles all the decisions, which handles controls the entire device. So it controls things. If you have a chassis, it controls the chassis, it controls power supplies, it controls the actual PFEs, which are the packet forwarding engines, which are line cards, which are ports, interfaces, where traffic comes in and comes out. So that component, the RE, is responsible for controlling all that. In fact, if you have high availability, you would have two. You would have one in active mode and the other one just waiting for the primary to fail. So it's very interesting, and it's better explained if we see a diagram to see how the RE and the PFE interact. So I'm going to draw it out here. So remember, the RE controls all the control plane, which basically is, like I said, all the device, routing protocols, management. So everything that you see as an administrator. It's where things like the routing table lives, the OSPF database, things of that nature. And then the PFEs, which sit down here, control, basically, it's where traffic comes in and comes out. And they have a couple of functions that we're going to talk about in a little bit. But think about it that way. Think that it's basically where traffic comes in and comes out. It's basically the cards. So basically, for example, like I said, here we can have like routing tables and forwarding tables, and it's basically the OS. So the PFEs also have some functions that are done in the actual line card to help being able to move more traffic in a more efficient way. So think about it. If you have like a chassis system and you have a line card that has 10 gig ports, then imagine that you are pushing all of that traffic. If that traffic, for example, in this part of the diagram, this is an internal link. If it was a chassis, it would be like the backplane or the share bus or the fabric or whatever it's called in that particular device. So it would have to go through this. So all of that traffic would have to go to the main CPU or the main CPUs in the RE and be processed. So that wouldn't be very efficient, and it would probably diminish the amount of throughput you can move, the amount of traffic you can move through that device. So in higher end devices, the PFEs have something called ASICs, which are specially built chips that handle very specific functions to be able to move traffic as fast as possible, to be able to fulfill wire rate. So, for example, the PFEs typically are able to handle things like quality of service markings, are able to handle things like stateless firewalling, that are typically be able to handle like policers without state. So the interesting thing is that if I'm pushing 10 gigs or 20 gigs or whatever amount of traffic down here, let me change color there so it's easier to see. That traffic goes straight through a PFE and doesn't have to go to the main CPU, which allows us to move a lot more traffic than it would have to go through the fabric or the share bus or whatever part of the device. So the interesting thing, like I said, on higher end devices, there are specific chips done for that, and that's basically, if you think about it, that's basically the difference between a lower end device, for example, like a J series router, where the PFE, part of the function that happens in the PFE happens in software, which means that it has to hit some CPU instead of like specific chips. And that's the reason why you might have, for example, line cards that are much more expensive than others. It's because they usually have more functions directly on the line card, so you don't have to go to the main CPU, which means that you can push traffic without having like oversubscription. So if you have 48 ports, you can move 10 gigs through all of them without dropping anything. So that's the interesting thing. Of course, there's exceptions. For example, traffic that goes directly to RE without going through without not being able to cross through the PFE is things like, for example, any traffic you send to the management of the device, or for example, like OSPF packets or that sort of thing. And in fact, in this internal link, there's typically some protection, some internal protection to avoid like DDoS attacks, where you just, where you send whatever a bazillion packets directly to the CPU of the device, and you overwhelm it. So. And you can typically configure more. So, for example, you can have devices that don't reply to any echo request, or, that don't take 1,000 updates, 1,000 OSPF messages per second, or things of that nature, in order to protect your control plane, because in the end, it's the brain of your device. A device without brains is typically very bad. So I think that's all for this video. So thank you.